Miss.
Oh, I may record. Okay. Good morning, everyone. We are Team Tacoma 2, and we're here to show our research on Tacoma Bridge. Our team consists of Richard, Lynn, Julia, Jack, and Frankie. And now I will show the basic composition of our presentation. Firstly, Jack will introduce the motivation and objective of our research and the background information of our two bridges. And then Frankie will show our failure experience, and Richard will show the main methodology and approach of modeling. Next, I will talk about the results and discussion of our research. And finally, Julia will talk about the summary and conclusion. And finally will be the contribution of our each member. So first, let's welcome Jack to introduce our project.
OK， 不用我的，用这条机麦克风。OK， let's begin with a video about Tacoma Bridge. We download this video from the internet. Since the whole process of collab lasts 4 hours, we only cut a short clip from the video. In this short video, we can observe that the bridge move up and down vertically with a stable frequency. It has a terminology name that called as torsional movement. In our study, we follow the code of the phenomenon. Tacoma Narrow Bridge, also known as galloping bridge because wind caught it move vertically. It was located in Washington State in the Pacific Northwest. The bridge connected the Olympic Peninsula with the mainland of Washington State at its two ends. At the third known, as the third longest suspension bridge at that time, it was 1,524 meters in total length, 583 meters in main span, 11.9 meters in wide, and 59.4 meters in clearance below. Using Moise's design, the construction began in September 27, 1938, and it opened for traffic in July 1, 1940. However, in November 7, 1940, it collapsed under the wind of 42 miles per hour. The main span, which was long 2,800 feet, went into a series of torsional oscillation whose amplitude increased gradually at 8 a.m. Eventually, at 11 a.m., the convolution tore several suspenders loose and the span broke up. Fortunately, no one died in the collapse of the bridge, except for one dog who is too frightened to escape from its owner's cars. This slide of PPT demonstrates our team inspiration of our project. C2 Bridge was constructed at the same period of time as the Tacoma Bridge. However, as the Tacoma Bridge collapsed only 4 months after it opened, C2 Bridge are still in use busily nowadays. The first picture is Golden Gate Bridge. It was built in 1937 and has a length of 8,918 feet and a height of 746 feet. Another one is George Washington Bridge. A double-decker suspension bridge have similar structure with Tacoma Bridge and connected New York City with New Jersey. Construction of George Washington Bridge started in September 2021, 1927, and the bridge opened in October 24, 1931. It had a total length of 4,757 feet with 3,500 feet in longest span, wide of 115 feet, height of 304 feet, and a clearance of 76 feet below the mid-span. Today, George Washington Bridge is still an important corridor within the New York metropolitan area. In this research, our group had many two objectives. Firstly, we want to investigate the vibration mode of Tacoma by ANSYS, and we experienced many challenges in order to reach the objective. After that, we are going to compare Tacoma with George Washington Bridge, one of the inspiration of Tacoma Bridge in terms of their vibration frequency and the total deformation.
And the second part will be methodology.
Okay, I thank to Jack's presentation. Now is the original time. Before I want to talk about more seriously, I just want to mention you some basic information about the Tacoma Bridge. As you can see from these pictures given by the authority net, the Tacoma Bridge can roughly divide it into the two main parts. The first one is the concrete construction, which including the main body of the bridge and the two girders. And the second parts are made by the construction steels, and you can see here the staining cables on the both sides of the bridge, and the perpendicular cables on its length. According to the official information, you can see that the Tacoma Narrow Bridge is a suspended bridge, and the total span of it is 1,550 meters, 850 meters in the middle, and 350 meters on the both sides. And you can see from the side view that it is 2 meters in wide and 2.0 meters in deep. Okay, this is the design. Okay, this is the design picture of the girder of the Tacoma Bridge, and you can stand here and look the girders in this directions. You can see that it's 60 meters in wide, and the total deep is 160 meters. In order to figure out some construction delays lead to the breakout of the Tacoma Bridge, our teams want to create another bridge which called the George Washington Bridge, and this is created in the 1940s, so that we can make a comparison between them and to get the conclusion. And you can see from the overlook of the George Washington Bridge, it's very similar like the Tacoma Bridge. It's also a suspension bridge, and the total span is almost 1,500 meters. Is very close to the span of Tacoma. And here is the girder of the George Bridge. The 50 meter in wide, and the total deep is 185 meters. Okay, I want to talk about more seriously the procedure of modeling. As you can see from the first picture that there are three rectangles. It's very easy for us to create this rectangle because they have the regular functions. This is the main body of the bridge, and here is two girders. And next, we will use the point function to draw many points on the edge of the bridge. And each point will divide the edge into the same space per 25 meters. And after drawing many points, we will use the function called the line from points and link the points to create the line, many lines which represent the cables. So it is very, and you can see from in this picture, the cables on the right hand side and the left hand side are straight lines. Finally, our team should to create the cables above the middle part of this bridge. But you can see from this, the cables are not straight lines but quadratics. So here our team face a confusing issue is that if when you create the cables above them, the connecting points will be moved right or move left randomly. And secondly, it's very hard for us to divide the quadratic line into the same space. So in order to solve these problems, finally our team decided to use the straight line to replace the quadratic lines. So here we use a method called the finite different methods we learned before. And here is the introduction of the finite different methods. And you can stand in the front of the Tacoma Bridge in the picture 1. Firstly, we stipulate the middle point and at the bottom of the first girder, it is equal to 0. And for the another girders, here points is equal to 0, equal to 1. So next we have our boundary condition from 0 to 1. And secondly, in order to create the straight lines, we need exact solutions. So we have an exact solution when x equal to the 1/2 on the quadratic line. So next we will link the points when x equal to 0, this point, and x equal to 1/2 this point. And in the same ways, we can get another line like this. And the green shadow area represents the areas between the exact solutions and approximate solutions. Okay, in the picture 3, there are more Nowlan points on the quadratic line. So sorry, sir. You can see that in the picture 3, you can see that there are more Nowlan points on the quadratic line. So there must have more straight line to replace the quadratic lines. The picture 4 are also the red one are newly built. So next we can guess that if there have the sufficient points from the 0 to 1, there must have more straight line to replace the quadratic lines. And from the picture 2, 3, 4, we can see that the shadow area above them are becoming smaller and smaller. So which is also means that the error of the exact solutions and approximate solutions will are equal infinitely. So this is the finite different methods, which is the most indispensable in our modeling part. After use these models, the problem we faced before will be solved. Okay, this is my part of modeling. So next we will welcome Lin to his analysis part.
So now we download the model and transform it into function and we will stipulate the material materials for different part of model. We use the structural steel for cables and concrete for the surface of the bridge and the girders. Next, we will connect the cables and the surface of the bridge by using joint function. Next, after we match them with 2000 millimeters, we will set up the fixed point at the bottom of the girder. And finally, we can get the total deformation of the analysis on ANSYS. Next, Frankie will talk about our field experience.
Okay, morning. And this is my part. So, and when I go into our field experiences, it's the one of the most interesting parts of all the project. So that's the first thing. Okay, fine. So first, I call it using a curving cable. Initially, we just make a circular arc from this side to another side, and we also choose the two vertices on the two girders so that we are able to join the circular arc passing through the 3 point. However, the trouble is that when we add one more perpendicular cable between the curve and the main road, it would cause the shift on another cable, other cables. So thanks Richard, he finds the finite difference method to solve this problem. Thanks Richard. Okay, so this part I would talk about is the vibration in fixed support. So the fixed support is this part. So you can see during the research, there's something uncontrolled error happens. Initially, we expect the vibration just apply on the main road, but we don't know why. The vibration happens at the middle of the fixed support. So when the vibration happens, the maximum strength point is same as the central point of the fixed support. So that's this is part. Next page. Okay, so this is the third uncontrolled error. It's the bending of the tiers. And in the process of the modeling, there was a mistake in some of the design frames. And so you can see the right-hand side girders. As for the other part, they still remain static. So in addition, a cable which is not connected to the girder, they still not follow with the frequency of the vibrations. But we also solve this problem. So the last one, that's an entire structure band inwards. So in last field experience, I want to say that after great value of time, we successfully placed the vibration point on the main body. However, when the vibration happens, obviously see that the entire structure shift inwards. So it's like this. It seems like there's a force acting downward vertically on the central of the main rod. So thus you can see there is a V shape at the maximum strength point. Okay, that's all I want to talk about in my field experiences. Lane, it's also your turn.
Okay, it's me again. I will present our results and analysis of our data. This slide shows the vibration of x-axis of Tacoma Bridge. As we can see, it's moved up and down, so we can say that it is caused by the stress on the surface, or pressure, sorry. And next slide shows the direction in y-axis. Since it's moved in the horizontal direction, so this torsion might be caused by the wind load. And from these two pictures, we can see that both of them has red part at the center of the span. So we can say that they have the maximum total deflection at the center of them. So we can infer that it's most fragile at the center of the bridge. So it's most likely to collapse under some stress. And this picture shows the George Washington Bridge's vibration. It's also in harmonic motion. This chart shows the frequency of the two bridges. As we can see, George Washington has much higher frequency than Tacoma Bridge, since we know that frequency is inversely proportional to period. So we can infer that Tacoma Bridge has much higher periods than George Washington, meaning that it will vibrate more time than George Washington in a fixed period of time. That may explain why it is more likely to collapse than George Washington Bridge. And this chart shows total deformation of our bridges. Tacoma Bridge has much higher total deformation. It has highest total deformation of 0.0705, and while George Washington only has 0.059, it's about more than 10 times than of Tacoma Bridge. So it collapses more. It is more likely to collapse. And we use millimeter as our unit because we take the scale of 1 to 10 for our model. And here is where we got the data from ANSYS. Next will be Julia.
So, well, I want to talk about, based on our research, we have further hypotheses about other factors that can cause the collapse of Tacoma Bridge. Well, firstly, it is the ratio of width and length. Since Tacoma Bridge has 1,600 meters and George Washington has 1,067 meters, they have basically the similar length. However, if we compare the width to them, it's only the George Washington Bridge has 3 times width of the Tacoma width. So if we calculate the ratio of the width of length, the Tacoma Bridge has the ratio of 1/72, but George has the 1/33. So it might explain why the Tacoma Bridge collapsed in only 4 months after its construction. And secondly, the factor might be the thickness of the bridge itself. So for Tacoma Bridge, it has only 2.5 meters for its thickness body, and George has 3.7 meters. So if we have the analogy comparison to the Tacoma Bridge, it will be more likely to seem as a thin and long spaghetti noodle. So it might explain why it is more fragile. And after I reading a lot of research papers that is written by other people, there are some scientists suggest that the reason for Tacoma Bridge to collapse is in its design. There's not a part of wind hole. However, compared to George Washington, there's a design of wind hole between its 2 desks. So when the wind speed reaches some limit velocity, it can pass through the holes. However, the Tacoma will only cause the torsional effect on the bridge body itself. And there are also some people suggesting that when constructing the Tacoma Bridge, the government, in order to reduce its cost and make the appearance more aesthetic, attractive, so they use the material that is cheaper and less dense compared to George Washington. So if we combine these 4 factors together, it might further explain is that for the wind speed for Tacoma Bridge, they also eventually result in the collapse of the bridge. And the 4th part will be summary. So basically, I divided our whole research project in 4 sections. So firstly, we modeled the Tacoma Bridge and George Washington Bridge for our further analysis and for comparison purpose. And secondly, in order to fix our failure models, we learn from our experience and we use the finite difference method to construct a proper and appropriate models for the analysis part. And thirdly, we can obtain the result from ANSYS that Tacoma is vibrating in harmonic motion when the wind is blowing on it. And finally, we can compare the Tacoma Bridge with the George Washington Bridge, and we can conclude 4 factors that might affect the collapse behavior of Tacoma Bridge. I also want to suggest that there are a lot of limitations in our research project since it is a short period of time. So firstly, we use estimated data for modeling. We have the data from internet that the Tacoma Bridge is actually 550 meters for the main span. But however, when we constructed it, we somehow manipulate the data and made it more convenient for us to make the models. And secondly, we have missed some error analysis part in our research project. However, when I read through those papers, I found our final result is similar to those results written in the papers. However, there are some errors existing in our research. And thirdly, this project lack of resonance analysis. Since it is a short period of time, we only do the model analysis for transient and the static. However, we didn't combine the vibration in z-axis and y-axis together, so there is lack of resonance analysis. And for our final part, I want to do some contribution assignment. So for Richard, he's in charge of modeling for the 2 bridges, and he ran the analysis and obtained the result. And he also writes the procedure part of report. So if we want to choose somebody to represent our team, it must be him because he's the spirit of our team. And for Lynn, she is in charge of collecting data, both in constructing the models and after analyzing the answers part. And also she helps me to create this amazing PPT. And thirdly, for me, I basically have the same work as Lynn. So I collect the data and I'm in charge of the literature review part of the report. And I also added the report together, and I'm mainly in charge of this PPT. And for Frankie, he's in charge of he's in charge of writing the failure experience part, both in report and in our PPT. And he helps with Richard to record and conclude the raw data that we obtained from our failure experiments. And for Jack, he researched a lot of background information, and he's in charge of background information part of both report and PPT. And he also collecting intro information for our research. So this is